I think we should go and get started. We're 2 minutes past the starting time.
Oh,
Okay. So if everyone could mute themselves, if not, Jessica will. Good afternoon. I'm Philip Stansel, the head of the Department of Physics and Astronomy at the University of Georgia. And let me welcome you to the Chhabra-Landau lecture. This is the second lecture in the series, which is an annual event now in our department. The lecture series was established by the generous donation of Dr. Ashwin Chhabra, who is on Zoom with us today. Let's see. So a little bit of background for Dr. Chhabra. He is the president currently of Euclidean Capital. He received his MS in physics from the University of Georgia, working with David Landau. And then he went on to Yale, where he received his PhD in applied physics. He moved into finance, where he was head of quantitative research at JP Morgan, and then managing director and head of wealth management strategies analytics at Merrill Lynch. He then became chief investment officer and head of investment management at Merrill Lynch. Now he heads the Euclidean Capital, which manages investments for the Simon Foundation, which you may know is dedicated to advancing research in basic sciences and mathematics. Dr. Chhabra established this series to celebrate David Landau's pioneering work in Monte Carlo simulations of condensed matter systems, and also for David's establishment of the Center for Simulational Physics. So let's welcome Dr. Chhabra and Professor Landau to this lecture. And thank him for sponsoring this. Okay, so now my pleasure to introduce today's speaker, our Chhabra-Landau lecturer, Professor Roberto Car of Princeton University. A brief few words about Dr. Car. Received his PhD in physics from Technical University of Milan, that's in Italy, and his career path has jumped across the Atlantic. He was at one time a research scientist at IBM Watson Research Center, and then he was associate professor of physics at Trieste in Italy, as well as professor of physics at the University of Geneva, and then at the Fritz Haber Institute as part of the Max Planck Society. He has a really long list of awards and accomplishments. And I just hit a couple highlights that are relevant today. One is he received the Rahman Prize for computational physics from the APS. He also received the Dirac Medal for International Center for Theoretical Physics, which you may know about because he shared this award with Michel Piranello, if I pronounced that correctly, for the development of ab initio molecular dynamics. This is the well-known Carr-Piranello method. He also received the Enrico Fermi Prize from the Italian Physics Society and the National Award in Theoretical Physics from Theoretical Chemistry from ACS. And in 2016, he was elected member of the National Academy of Sciences. And more recently, actually received the Benjamin Franklin Medal in 2021. Today, he is the Ralph W. Dornte Professor of Chemistry at Princeton University. So his lecture today will be on machine learning-based ab initio molecular dynamics. Let's welcome Professor Car.
well, thank you.
And take it away.
Yeah, thank you very much. And I'm really pleased to receive your invitation and to give this lecture. Let me try first to share the screen. And where is that? Now that, where is that? Why doesn't, let me do that. I did something wrong. Let me see now if it works. Yes, here it is. Share. And now I can put it over here. And let me see if I go into presentation. Yeah. Can you see it?
It's all perfect here. Thank you.
Okay, very good. So I was saying that I'm very pleased to be giving this lecture, and I'm highly honored to be the second speaker of in this distinguished lecture series. So today I'm going to talk about what has been my main activity in the last few years, basically using machine learning technique to boost ab initio molecular dynamics. Now, let me, first, before moving on, let's say this activity has been sponsored by the Department of Energy. And in fact, we have at Princeton what is called a computational chemical science center that is called Chemistry in Solution, and that interfaces and this technique based on machine learning have been developed in that particular context. So let me move on and try to, let's see, wow. Oh, I have to go over here. There is, so let me say a few words. For instance, here we see what is molecular dynamics. We see here a simulation box with periodic boundary condition in which molecules move. These are water molecules, and there are about 10,000 water molecules in this box. And what happens is that this is a simulation in which there is a crystalline nucleus or a crystal that form ice that has formed in this simulation. And this is a process that is a rare event, and so will not occur directly in ab initio in a molecular dynamics simulation. So what we do in molecular dynamics simulation, as this little movie showed, we solve numerically on a computer the Newton equation of motion for the particle in the system. The forces on the particle depend on the potential energy of interaction that depend on the coordinate of all the particles in the system. So that is basically what we do in a molecular dynamics simulation. Now, the simulation that I showed in this little movie was based on an empirical force field to describe the interaction between the molecule, and also used a special technique called metadynamics to facilitate the formation of the ice structure that you saw in the movie. So this is something that it is possible with force field based molecular dynamics, but until recently, it was not possible with ab initio molecular dynamics. What is ab initio molecular dynamics? Well, ab initio molecular dynamics is the same thing. So we are solving for the classical trajectories of the particle, but the potential energy of interaction, rather than being described by an empirical force field, is derived directly on the fly from the quantum mechanical ground state of the electron. Solving the quantum mechanical ground state of the electron is difficult, and so we need to use some approximation, and typically the approximation that we use is some approximate form of Kohn-Sham density functional theory. Deriving the potential energy surface from quantum mechanics gives the method a much better predictive power. However, it is also significantly more expensive than standard molecular dynamics based on empirical force field. What the machine learning technique do is that they allow to learn the potential energy surface from quantum mechanics and make possible then simulation that have the cost of empirical force field without losing the predictive power of quantum mechanics. So the little movie that I showed based on an empirical force field can be done today with quantum mechanically based potential with a simulation based that has learned from ab initio molecular dynamics. In particular, in my talk today, I will discuss one such method. There is a wide variety of machine learning methods that have been developed in recent years. This is becoming a hot subject. And I will discuss in particular one such method, which we call the deep potential method, because it is based on deep neural network to represent the potential energy surface. And I will show that it can also be used to represent other ground state properties that are accessible to ab initio molecular dynamic simulation. This technique has been developed, and the main driver in this technique has been Linfeng Zhang, a former student at Princeton who developed much of the method that I'm going to discuss today for his PhD thesis. He received a PhD about a year ago, and his work was directed by two persons. One was me, and the other was my colleague Weinan He, who is a professor in the math department. Several other people contributed to the effort, and I will mention them in the course of the talk, or some of them in the course of the talk. Let me move on and describe quickly what do we do. Basically, suppose we have a quantity, an observable quantity that I called O in this slide that depend on the coordinates of the atoms, all the atoms in the system. This quantity can be a scalar property, like for instance, the potential energy, or it can be a vector property like the polarization, or it can be a tensor property like the polarizability. And we call all these observable as a function of the many atom coordinate. We call these things surfaces. In the potential, in the deep potential representation, which is similar to representation with other neural network methods, we represent this property as a sum of atomic properties. The index I in the sum range runs over the atoms in the system, and each one of these atomic property is a function of the coordinate of the atom that belong to the environment of the atom I. The environment has to be defined and set a priori, well, based on trial and error, but typically the environment can contain, I don't know, 30, 40, 50, or even 60 atoms or so. And so it is a kind of generalized embedded atom approach for the representation of the potential energy, the polarization, and the polarizability surfaces. This function f, that is represented in terms of neural network, is a symmetry preserving, continuous and differentiable function of the atomic coordinates in environments that can have a variable numbers of atoms. Now, What does it mean, symmetry preserving? Well, of course, the symmetry of the environment must be preserved. So if we don't impose the symmetry, the scheme would not work or would require an infinite amount of data to learn. So the symmetry is that essentially is the translational, rotational symmetry of the environment, and also the permutational symmetry. The fact that if we exchange two atoms of the same species, the function should not change. So we have this symmetry condition that must be satisfied, and they are typically satisfied by providing in input to the neural network descriptor of the some descriptor of the spatial configuration in the system that satisfy this symmetry requirement. Now, in our deep neural network representation, we have some distinctive features that are the following. On one hand, we have a network that is very flexible, can represent well functions of that depend on many variables. We say that this deep neural network beat the curse of dimensionality. And another feature that we have is that we have developed a technique to learn on the fly, similar to what we do in the ab initio molecular dynamics. We calculate the potential energy or the forces on the atom on the fly from the quantum mechanical ground state of the electron. Here we want to learn on the fly the potential energy surface that describe our system in a given target range of thermodynamic condition. In addition, the methodology is very efficient computationally, and can be optimized for high performance computing performance. For instance, has been quite effectively optimized on multi-GPU platform that allow us to do rather large and complex system. So this is
Roberto,
yes,
sorry,
yes.
there's a question for you in the chat. Should I
Yes.
read?
Yeah.
Do you
Please.
still diagonalize H? Do you still compute single particle energies? And can you still distinguish between a metal and a band gap material?
Oh, I will say how we learn. In fact, we distinguish between we have to learn from DFT calculation. So in the DFT calculation, but the DFT calculation that we use are mostly single shot DFT calculations. So they are done similarly if I have a metal or if I have a, so we have to minimize the energy, compute the energy and the forces or some other properties. That has to be done. So we don't do it via ab initio molecular dynamics anymore. We do it by solving the Kohn-Sham equation for a given set of configuration by doing just single shot calculation in this for this set of configuration. But this set of configuration are generated by exploring the space with a trial model that as we keep exploring keep being improved. I will describe that in a moment. So please feel free to ask me a question if something is not clear and requires some additional. So today, in my talk today, I will discuss mainly application to a system made of water molecules. So water is a very fascinating and complex system. So the potential energy surface is just this quantity E, a scalar quantity E, and it is represented as a sum of local quantities. So this is a general representation for the potential energy surface for any system. But this quantity here, M, which is the cell polarization, and this alpha, which is the polarizability, they are written here explicitly for a system made of water molecules. And essentially, the cell polarization include information from the position of the nuclei, the oxygen and the hydrogen, but there is also electronic structure information. This electronic structure information is given in terms of the center of the maximally localized Wannier functions. And since the maximally localized Wannier functions are near the oxygen in our system, near one oxygen atom in our system, and they remain near the oxygen because the oxygen is more electronegative, even if the molecule dissociate, we can just consider the average of the four Wannier centers that are associated to one oxygen atom and consider this quantity W sub I, which we call the Wannier centroid. This Wannier centroid, of course, depend on the coordinate of all the atoms in a given environment of the atom I, which is the oxygen to which this Wannier centroid is associated. Now, these maximally localized Wannier functions are uniquely defined by a unitary transformation in the space of the occupied electronic state in our system. And here, I'm also used the fact that I'm using, I'm treating explicitly only the valence electron in the system. So the core electron are just frozen and added to the charge of the nucleus to form an ionic core. So the charge associated to the oxygen is 6. The charge associated to hydrogen is 1. And we have the charge associated to a centroid that is given by 4 maximally localized Wannier functions, each one of which is associated to 2 electrons of opposite spin. We are in a spin saturated system here. The charge here is 8 with a minus sign. The polarizability is simply defined as the derivative with respect to an applied electric field by keeping the position of the nuclei fixed. And so it's just given by this sum of tensors that are the derivative with respect to the electric field of the Wannier centroid. So these are all quantities that are accessible in a density functional theory calculation and would be also accessible in an ab initio molecular dynamics calculation. Let me move on. And now, a very important issue is to do as little density functional theory calculation as possible, because these are expensive. And so if we have to do a lot of density functional calculation in order to learn, then the method will not be as efficient as it can be. So in order to minimize the number of density functional theory calculation that need to be done to learn, we exploit one property of the neural network. And the property of the neural network that we are exploiting is the highly nonlinear dependence of the network from the network parameters. So here is an example of a forward neural network that has this form of a function of a function of a function, and the parameter are this coefficient, this vector b, and these matrices w. And these are the parameters that define the network. Clearly, the dependence of the network from this parameter is highly nonlinear. So if we minimize the deviation of the prediction of the network with respect to a reference system that is DFT in our case, we will get a different local minimum if we start with a different initialization of the parameter. However, if we are in configuration that are close to the configuration in which the network parameter were trained, the different local minima typically will describe equally well the physical property of the system. So that is true if we are close to the training data, but as we move away from the training data, from configuration that are away from the training data, the different local minima that we obtain will start to diverge. So we can use the following procedure. We have a model that has been based on some initial training, and we explore the configuration space of interest with a few representative models that have the same parameters, but differ only in the initialization of those parameters. As we perform trajectories with this neural network model, these trajectories are molecular dynamics trajectories, and they are very efficient. The cost is like a cost of an empirical force field. So we can explore different configuration, and we can monitor the deviation between the different representative model. When the deviation between different representative model becomes exceed a certain threshold, we say we have maximal disagreement between the models. It means that we need to acquire new data. So we label that configuration, and labeling means that for that configuration, we do a DFT calculation, we obtain the potential energy, and we add this potential energy to the training data set, and we improve the model. And with the improved model, we go back to exploration, and we keep doing this cycle until we reach convergence over the entire configuration space of interest. So we only do, at this point, single shot quantum mechanical density functional theory calculation for the labeled configuration. How much more efficient this approach is than starting to do a lot of ab initio molecular dynamics calculation and then learning from those? Well, it is significantly more efficient, because if we do ab initio molecular dynamics calculation, there will be high correlation among the data that are at different, at closely separated time step in the molecular dynamics simulation. Instead, in this way, we will label. Typically, we label configurations that are sufficiently well separated in time so that they are essentially uncorrelated, and typically, in our experience, less than 1,000, between 1,000 and 10,000 of the visited configurations are labeled. So we explore a large number of configurations with an effective method, but only a rather small subset of this configuration is needed to improve the model. So that is the technique that we call deep potential generator. Now, having described quickly what the technique is about, let me show you, illustrate the technique with some example of recent work. Well, of course, I've been rather quick in explaining what we do. I didn't describe in detail the characteristic of the neural network model that we use, and so on and so forth. But basically, the neural network model, what it does is that it provides an interpolator between different configuration in a highly dimensional space, and the expression in terms of a sum of atomic contribution gives this neural network model by construction extensive character. So a model that has been trained on relatively small system for which DFT calculation where possible can be immediately transferred. Well, we have to check a number of things, but it can be transferred to a much larger system. So now let me just show you some few examples. Basically, having this powerful proxy for ab initio molecular dynamics, I can now do many studies that were beyond the reach of direct ab initio molecular dynamics simulation. I will discuss few examples. One is the phase diagram of water. What does this scan means? Well, this is a particular approximation. Is a special approximate DFT functional that was introduced a few years ago by John Perdue, and which is a quite accurate functional, and we use that in the calculation that I will show. I will discuss the phase diagram. I will discuss the auto-ionization of water. I will discuss a classic problem, the order-disorder transition in ice. And finally, I will present a few results on vibrational spectra. Let me discuss the first example. So in this first example, we have been able to train a neural network model for the potential energy surface that works in this rather large range of thermodynamic conditions. So we have temperature here ranging from 0 to 400 Kelvin, and at this higher pressure ranging from about, well, from the 400 up to more than 2000 Kelvin. And the pressure, in the pressure range, we go from atmospheric pressure up to 50 gigapascals, so pressure that can be important in the mantle of the planets. Now, so this is a rather large range of thermodynamic condition. We have here fluid phases. I call it F, the fluid phase. So this is the standard liquid water. But in this condition here, at high temperature and pressure, this is an ionic fluid in which a significant fraction of the molecule is dissociated. So the same neural network is able to describe all this structure. And since the calculation is the calculation then is quite efficient once we have the network, we could predict by using standard techniques, we could predict the phase boundary between the different phases. So you see there are a number of crystalline phases. Here there is hexagonal ice. This is ice 11. This is ice 2, ice 6, ice 5, 8, and 7. The red line are the lines that are predicted from the deep neural network model. They are close to what would be the prediction from the direct DFT calculation, if we were able to do it with the same approximate function, also this scan functional. Typically, the error in the free energy prediction that we have is the error in terms of deviation from different representative neural network with the same parameter, and error relative to the DFT calculation is approximately of the order of 1 milli-electron volt per molecule over the entire phase diagram, which is quite good. But of course, there are deviation from experiment because the density functional theory is not perfect. But so we have here experiment. The gray line corresponds to the experimental phase boundary. And you can see that the agreement is rather not bad given the complexity of this system. There are some phases that do not come out. For instance, this ice 3 is only metastable in the model. And similarly, this ice 15 that is present in experiment is only metastable in the model. But, and also other properties, for instance, the melting is around 310 or so Kelvin, rather than being at 273. However, all this calculation here has been, all this structure here has been predicted with classical molecular dynamics simulation. We know that nuclear quantum effect or quantum fluctuation of the atoms will affect the phase boundary. We know that because of the isotope effect that are observed in experiment. And so we expect that by including this quantum effect of the nuclei with path integral simulation should improve somehow the agreement with experiment. However, the effect coming from the nuclear quantum effect probably should be smaller than the deviation of the model from experiment that is related to the inaccuracy of the DFT functional. Here, I just reported in blue in this figure here is the phase diagram predicted by popular model for water, for an empirical force field for water that has been based on experimental properties at relatively low pressure and so at relatively low pressure, this model does a relatively good job, but the disagreement with the experiment is similar to what we get in our calculation. And but it starts deviate from experiment quite a lot as we go to high pressure. And in fact, in this model, there are not ionic phase possible because this model is based on molecule that cannot dissociate. And so there are, for instance, there is this plastic phase that is predicted here for which there is no experimental support.
Excuse me,
Roberto,
Roberto.
can I
Yes.
ask a question, please, Roberto?
Yes.
So I'm trying to understand what it is that you're predicting through your neural network, because in the 35,000 one-soft DFT calculations, I'm assuming that you've done as part of your training set the
Yes.
DFT calculations for these various different ice solid state phases. So those are not predicted. Those are put in as part of your training set. So it's really the boundaries that you're trying to define through your
boundary. Yes, you are right. The phases. We use the crystalline structure of all these things, and we have explored the thermodynamic range more or less uniformly in this exploration feature, and in this exploration we needed of the order, well, less than 35,000 DFT minimization to construct the PES, which is this relatively small fraction of the total number of fitted configuration. So the boundaries are predicted by computing the free energies of with thermodynamic integration and locating boundaries between different phases by doing that, and then integrating, for instance, the Clausius-Clapeyron equation to continue a boundary line and things like that. So we use a number of standard techniques to locate the boundaries and which require calculating the free energy of the competing phases.
Thank you.
You're welcome. And well, I see that it's taking a little bit, I have too much stuff. I will try to cut out something, but let's say just one thing that is quite interesting that we could do with this thing. For instance, here at high pressure, one has this phase that is called I7. This I7 is still a molecular phase in which the oxygen form a BCC lattice. And you can see there are two hydrogen close to this oxygen here in the center, and there are two hydrogen close to this oxygen, one hydrogen close to this and to this. So each molecule is in a tetrahedral environment. These are the hydrogen bond that keeps this system together. And this hydrogen, there are two close and two further away from each oxygen. This constitutes the so-called Bernal-Fowler ice rules, and they are satisfied in I7. What happens if I increase, if I move along an isobar, varying the temperature? That is what happens, what is shown here. And this is an isobar somewhere over here. I don't remember what is the, well, should be something like 15 or more gigapascal. So if we move along this isobar, what we see that there is onset of the hydrogen diffusion that we can measure in the simulation. And so it means that temperature partially dissociate this molecule, breaks the ice rule, and allow the hydrogen to diffuse around. And this hydrogen that diffuse around, let me see, I lost, oops. I don't see very well, and and the cursor. So anyhow, what happens is that the hydrogen diffusion increases and then saturates and remain saturated for a certain time, and then eventually also oxygen start to diffuse, and there is a jump also in the diffusion of the hydrogen. So what happens is that this system that was initially a molecular crystal has in the end underwent melting to a partially ionized fluid phase, but the melting process is a two-step process in which the system underwent a superionic phase in which the sublattice of the oxygen is still crystalline, but the hydrogen sublattice is diffusive. The onset of this superionic phase, the diffusion increases continuously. So this would be what is called a type 2 superionic material, in which the diffusivity increases continuously. And what happens if we consider how the enthalpy of this system vary? The enthalpy of this system here varies, has a more rapid variation in correspondence with this saturation here, but we can go reversibly in the simulation that we do with this system, up or down this curve. So what kind of transition do we have there? Well, this was obtained with simulation with a 432 molecule, but we could do simulation with a significantly larger system, for instance, 3,500, almost 3,500 molecule, and we see a sharpening of the transition, both for the enthalpy and for the volume of the transition. We understand where this thing comes about, and so we can say that this transition is a weakly first order transition, and we call the superionic phase I7 second, and I7 is the molecular phase here. And just to confirm the weakly first order phase of this transition, which is also confirmed from recent experiment, this is difficult also in experiment, we needed to go to larger system sizes that would definitely not be possible with direct ab initio molecular dynamics simulation. So this is one example. Now, the second example that I want to discuss is this ionization of water. A very important process is the self-ionization of water. It's also called autoprotolysis. And essentially, if we have a reaction in which two water molecules give rise to two one negatively and one positively charged ion. This negatively charged is called the hydroxide, and the positively charged is called hydronium. Now, in the liquid water environment, at any instant, only two water molecules over 1 billion of water molecule appear as ions. And this is the reaction that is at the basis of the pH of water. And the constant associated with this reaction is what is called Kw, and gives the product of the concentration of the two ions that in standard in pure water are the same. So,
Excuse me, Roberto, there's a
Yes.
question from Jim.
yes.
Hey, sorry, Professor. You mentioned that it wouldn't be possible to do the DFT on something of the size of like 200,000 molecules. Why is that?
Well, it would be, these are simulation with 3,000 in order to get the curve that I showed before with more than 3,000 molecule. We had simulation of several nanoseconds at each thermodynamic condition along this curve in order to get a good statistical error. To do it with direct DFT calculation, it would be impossible, I think, even if you have the...
Is the calculation recursive?
Well, you have to solve, you have essentially to diagonalize the Hamiltonian, and will be a rather large Hamiltonian in a system that has, you have to do a self-consistent diagonalization of the Hamiltonian for a very large number of configurations. So you
But
have,
if you're using a GPU, like I would assume you would parallelize that.
well, but there is, you can do a calculation with GPU and this kind of thing if you have with 3,000 molecule, sure. But consider I don't know, 10 nanosecond, a trajectory of 10 nanosecond. 10 nanosecond, and you can do to do that trajectory, to integrate that trajectory, you will have to integrate the equation of motion over with a time step of the order of a few femtoseconds. You divide the nanosecond by the few femtosecond, and you get a very large number, zillion of DFT calculation that you need to do. So just a single DFT calculation you can certainly do, but as many as you need to compute this property with good statistical error would be impossible, I think.
I mean, sorry, to me that seems like it would take a couple hours on like a P100 NVIDIA GPU.
Well, if you can do that in a couple of hours and not in 100 years, I would give you the Nobel Prize if I could.
I'm just misunderstanding where the...
No, I don't think it's possible. I don't think it's possible. I think it's, I mean, there is a difference between a calculation for a single configuration and integrating a molecular dynamics trajectories. You have to go through a very large number of configurations. Here we are computing statistical properties, not ground state properties, but statistical properties at finite temperature and pressure that require extensive sampling.
So how many calculations do you need to do per time step?
A time step is, if I do a per time step, a time step is let me go back to the curve here. So I said, for getting each one of these points, we need to compute, to evolve the system for a time of the order of several nanoseconds.
Mm-hmm.
In a time step is, let's say, 1 femtosecond. So if you 10 to the minus 15, and the nanosecond is 10 to the minus 9. And so let's say we have a million calculation for each one of these data points. There are maybe 10 data points. We have to do 10 million calculation just to do that.
That's just not a lot in the terms of like a GPU step.
Well,
But you're just saying that it's so many steps.
We are using GPUs, and we are even using. We have a big project. So we have a big project with GPU on Summit computer, and we are also using a code that has been developed at UC Berkeley to do some well. With the deep potential, here I want to focus on the physics, so I will not,
Sorry,
but with the deep potential, we can do millions or even 100 millions of atoms. Can you do that with DFT? And for nanosecond.
Oh yeah, it's a lot for both of them combined.
So however, to get some physics out, is not sufficient to do million, but you have to look at some properties. So sorry, I would like to say a few more things.
Yeah, no,
and
please go on.
We can discuss. So let me go more quickly. To make the story short with this thing, let me move on. And basically, what I want to say here is that in this case, we have studied with enhanced sampling technique, which is metadynamics in this case, the dissociation of the water molecule in water. And this is a process that will not occur in your molecular dynamics simulation if you let the simulation evolve spontaneously, even if you wait for 1 year or even for 100 years, you will not see it because it's a rare event. And well, I said that we have it involve 2 molecules over 1 billion molecule, and so that will not happen, but using enhanced sampling technique, and we can compute the free energy again, not the energy, the free energy, and we can compute the free energy associated to this dissociative event. And the free energy associated with this dissociative event is a free energy that depend on size, and in fact we could converge on size. Here we have convergence on size with about 1,000 water molecule, but each one of the simulation that we need to compute this free energy involves again simulation of the order of tens of nanoseconds in order to be converged. And the result of that simulation is that here we did the classical simulation, heavy water at 330K. We get this quantity that is called the pKw. The pKw that we extract from this simulation is 3.6. And the experimental one for heavy water at the same temperature is 13.9. You know that the pH of water, this is pKw is essentially twice the pH if we have pure water, and so the pH of water is 7. So we can predict rather well this property. I was quite amazed when I saw that result. It involves a rather complicated calculation, and now this was obtained with classical DPMD. We are currently performing quantum mechanical calculation with Feynman path integral in order to get a value for light water, and also to see if if we can predict the isotope effect that is observed in experiment. So this is another example. Let me go. Well, I don't know how I can go with the time. I can go on, but
Keep going.
please let me know.
Okay, go ahead.
So I want to discuss in a little bit more detail, but this is a classic problem in chemical physics. The disorder transition is in hexagonal ice. So the ice that we have a standard thermodynamic condition is hexagonal, and that is also the reason why the snowflakes have this hexagonal pattern. Now, in the 1930s, Joke at Berkeley made some very important experiment in which he discovered that ice had a residual entropy as the temperature was approaching the absolute zero. Ice that was supposed to be a crystalline material had an entropy that he extracted from experiment a value of 0.41 K Boltzmann. Now, at approximately the same time, Bernal and Fowler established the ice rule that I mentioned before, that essentially state that how the hydrogen can be distributed in the bond in order to have intact water molecules. And so Bernal and Fowler established this ice rule and pointed out that the random orientation of the water molecule was conceivable in presence of a crystalline arrangement of the oxygen atom. So it was possible to have oxygen that had a crystalline distribution, and at the same time having a structure with intact water molecule that satisfied the ice rule. So it was possible to have disorder in the system, and in fact Pauling did a simple mean field calculation, actually a calculation what is called, we call a back of the envelope calculation, in which he was able to compute the number of disordered proton configuration approximately, but he could get from this from its calculation a prediction for the entropy associated to the disorder in the proton of 0.405, so very close to the experimental value. This was a very important experiment and very important result, because it showed at the beginning, when they first made this observation, there was the issue, well, is the third law of thermodynamics violated, that a crystal, a ground state system can have an entropy that is not zero at the absolute zero? Well, there was no violation, because in fact one has a disordered distribution of the proton. One has something similar to a glass for the proton. But then the question arises, does an ordered form of ice exist? And again, very famous people suggested that it could exist, an ordered form of ice, but it was kinetically hindered in experiment, because in order to rearrange the proton in an ordered way, you have to break the ice rule, and that can only happen if there are defects that allow that to happen. And the defect can be either ionic defect, this hydronium hydroxide, or defect associated with rotated water molecule that are called Bjerrum defect. And in fact, Onsager even suggested that doping ice with hydrogen fluoride could facilitate the process, because the hydrogen fluoride could dissociate, and that could donate a proton to the ice, and having created an ionic defect that will allow this defect to move around and modify the order of the proton in the structure. But that didn't work. And finally, in 82, a Japanese group found that the transition to an ordered phase occurred by doping with potassium hydroxide, and so now it is well established that there is an ordered structure of ice in which the protons are ordered, and in fact the order structure is ice 11, and it is a ferroelectric structure because the dipole of the molecule are preferentially oriented in a direction. Now, here what we did was to try to describe this structure, the structural transition with molecular dynamics. It can be done with Monte Carlo, but we tried with molecular dynamics. And how we do that? We do that by using enhanced sampling and a suitable collective coordinate. And so far we found two of these collective coordinate, one collective coordinate that favor the appearance of hydronium that move without introducing a potassium hydroxide, simply move a proton away from one molecule into another molecule, and then this pair of hydronium and hydroxide that are created in this system can move around and eventually recombine. If they recombine by going through a series of hydrogen bond in a hydrogen bond loop that is entirely contained in the simulation cell, they will change the orientation of the dipole. Sorry, they will not change the orientation of the dipole, but they will do it if they recombine along what we call the winding loop, so a loop of hydrogen bond that closes via the periodic boundary condition in the system. Creating this defect allows for changes in the structure of the ordering of the proton. However, you can see here there are simulations in which we create those defects, and we see how the system evolves after we create this defect. If we start from the ferroelectric structure, so from the order structure, it goes down to the disorder structure. If we start from the disorder structure, it stays in the disorder structure. So again, we are in a situation in which we need to use enhanced sampling and use another collective variable in order to favor the reversible transition from the two structures. That we could achieve. Here, this is the order parameter that we are using, that is the number of local related to the number of local ICE 11 configuration. And at this high temperature, 300 K, we have a sampling. When this is equal to 96, we have 96 molecules in this system, so a small system. And in this simulation, we see a lot of reversible transition between the order and the disorder. And you see these are 100 nanoseconds. The transition becomes less frequent if we reduce the temperature. And in fact, with what we have so far, we are not able to go below this temperature. We have to improve something on the order parameter and on the sampling of the model. But already with what we get with this simulation, we can see that we can map the free energy. Of course, the free energy at this high temperature, the system, disorder is more stable, and we have this variation of the free energy as we go to the order structure. And we can extract the entropy from this thermodynamic relation, and that is the entropy that we obtain with the error bar. The error bar becomes larger if we go to lower temperature. Essentially, this entropy is a configurational entropy. It doesn't change much with the temperature, and we see these are a result that agree. Well, Pauling is this estimate here, but Pauling is a lower bound for the entropy. Nagel is a much more accurate calculation. Our calculation within the error bar agrees with Nagel and agrees also with experiment, but we should study the size dependence because this entropy should be reduced with size. I want just to show you this picture here. This was obtained by monitoring, by calculating the free energy as a function of the polarization, because the polarization is established in this transition from paraelectric to ferroelectric phase. And we can see that this order parameter is polarization has much more resolution than just the order parameter that we use in our simulation, and has this structure that reminds us that there are the changes in polarization involve overcoming barriers that are needed for moving this defect around. So this I think is the first calculation in which the entropy was calculated, the configurational entropy was calculated by using knowledge also on the energy. Of course, the energy is not really important in this case because all these structures have approximately same energy, but the energy, or more accurately the enthalpy, was included in this calculation, and we get results that are close to the experimental number. And what can I say? I wanted to show that there are still lot of progress to be made in order to capture the relevant physics in a problem like that. We would like to improve the sampling, we improve the collective variable that we use, and do a study as a function of system size, and also at being able to go to lower temperature in the simulation. Let me just show one very last slide. I mentioned that we can compute vibrational properties, vibrational spectroscopy, for instance, infrared absorption and Raman scattering. And essentially, the calculation of these dynamic properties involve the calculation of this time correlation function. Here is the polarization, and here we have the polarizability. Here we consider the anisotropic part of the polarizability. And again, these are calculations that would be possible with direct IMD simulation, but one would not be able to get a signal as clear as this one, because one would be able to do shorter trajectories and have more noise in the calculation. We can see here that we get a rather decent agreement with experiment, and particularly this one that are due to Raman. These modes, you see the frequencies of this mode are here in this low energy range of the vibrational spectrum. These modes have an intensity that is of approximately 2 orders of magnitude smaller than the intensity of the Raman signal in corresponding with the stretching modes. So these are detectable from experiment, but from ab initio MD simulation, the noise would be so large that one would not be able to see them. Instead, we can see, and we can even study the temperature dependence that is related to the breaking of hydrogen bond as the temperature is increased, and we see the same trend that is observed in experiment in the simulation. Of course, to have to reproduce very closely the experimental result is difficult. Also because of the approximation in the density functional theory to get the polarization and to get the polarizability that is a derivative of the polarization. The polarizability is an even more delicate property to get. That was just to give you an idea of what one can do with this kind of methodology, and I apologize for having abused your patience, and let me just mention a few, make a few comments. Deep potential molecular dynamics is several orders of magnitude more efficient than direct ab initio molecular dynamics. In fact, it is 4 or 5 times, 5 order of magnitude typically more efficient, and has linear scaling with size, which opens the way to studies that are well beyond the reach of ab initio molecular dynamics. One can study complex phase behavior, ferroelectric behavior, nucleation, catalysis, and so on and so forth. Now, deep potential is a proxy for density functional theory, and therefore quantification of the model deviation from the reference is important, and algorithms to achieve this goal are crucial. For instance, the spread of the network ensemble, which I discussed before, the reweighting of deep potential data in order to get to weight them with the Boltzmann factor associated with DFT, and so on and so forth. All these techniques are quite important. There are a number of issues apart from the issues of sampling that I mentioned in discussing the order-disorder transition in ice, and one issue is long-range electrostatics. In the standard formulation of this deep neural network, even one has an embedded atom form in which the interaction have finite range, because the energy contribution of a given atom it depends only on the coordinate of the atom in a finite environment of that particular atom. That is what gives rise to the extensive character and the linear scaling with size. But there are phenomena that depend on long-range electrostatic effect. We know that there are charges in the system. Of course, typically systems tend to screen these charges, and so in condensed phase, in many instances, they are not important, but there are instances in which they are. For instance, the longitudinal transverse splitting of the optical phonons in an ionic crystal in the long wavelength limit will require long-range electrostatic and will not be described by the network that do not include that. Also, there are quantum effects that I mentioned that can be treated with path integral. And then there are more difficult issues. The correlation function, time-dependent correlation function that I showed were calculated with classical trajectories, but we know that when there are light atoms, there are quantum correction to that. And so this is an open issue, how to include this quantum correction. And there is also the issue of the accuracy beyond density functional theory. And with that, I would like to thank you all for your attention, and again, apologize for exceeding the time that was allocated to the lecture. Sorry.
Thank you very much. Fantastic.
Yeah.
Well, thank Dr. Carr.
Yeah.
All right. Do you have any questions? Let's see if
I'd like to ask a question, if I might, Philip.
Go ahead, David.
First of all, this was a beautiful description of a fantastic advance using molecular dynamics. It was very impressive. I noticed that the plot that you showed of the free energy versus polarization looks very much like the folding funnel that you often
Yes.
see for protein folding and all of
Yes.
the complexity.
Yes.
We've had a good deal of success using modern Monte Carlo methods
Mhm.
for statistical mechanics models of such systems. Would you like to hazard a guess about the potential utility of using Monte Carlo together with machine learning?
Yes, I
Manner
think that would also be very useful. I think I must say, just make a comment regarding to that. That was, I mean, disorder transition in ice is one of these classic problems that always fascinated me, and so we started looking at that. This paper that will appear in Molecular Physics is actually a paper that appeared for a special issue to honor Mike Klein 80th birthday. So we didn't have much time to analyze the result, but that is definitely something that looks fascinating. Well, you can say looks like a funnel in the protein folding, but also looks like, I mean, yeah, this is a funnel because there is a transition from a state that is polarized, that is ice 11, that at this high temperature has higher free energy, but it will have lower free energy if we go below the transition temperature, but we were not able to do the simulation because of sampling. And so maybe with Monte Carlo, we can improve on that. We are thinking of using technique like replica exchange and techniques of that kind in order to improve the sampling. But also we think that the order parameter that we have used probably could be improved. So definitely there are a number of things that we would like to understand, and the fact that there are these barriers to go to this different state is related to the fact that there are certain group of molecule that change the orientation at the same time and cause the polarization to change by a notch. And but in order to do that, there is a barrier to be overcome. So that's something that looks quite fascinating, and definitely would like to understand more.
Great. We have a question from Jason Terry next.
Yes.
Yeah, so thank you. That was great. So my question pertains to your active learning pipeline. So
yes.
You're training all of these models and you have this reference, and obviously the whole point is to make them all agree to a very high degree. But that agreement isn't going to be perfect ever. So
Yes.
in
No, it's never
practice,
going to be perfect. However, we have done some study, more accurate study again with Pablo Piaggi, who is a postdoc who got his PhD with Parinello and is at ETH and is extremely good. And we have done some, we are applying this technique to study ice nucleation. And in this study of ice nucleation, we had, we have in fact a paper that will appear soon in Journal of Chemical Theory and Computation, in which we study a number of thermodynamic properties of the neural network model. And we have been able, for these thermodynamic properties that include, for instance, a property that is then very important for the nucleation, that is how the difference in chemical potential between the liquid and the solid change with the undercooling temperature. And we have been able to study what would be the so these studies were done again using a variety of enhanced sampling method. In particular, we use multi-thermal, multi-baric sampling, and based using variationally enhanced sampling. So multi-thermal, multi-baric means that with a single trajectory, we can sample configuration that describe a finite range of temperature and pressure with a single calculation, with a single trajectory. It is more efficient than doing separate trajectory at the different thermodynamic state point. And in that calculation, we could also do reweighting of the Boltzmann factor that govern the averages and extract the Boltzmann factor that we will have for those configurations with DFT. We have and that was only possible because the potential is rather close to the DFT calculation. To make the story short, we found differences, for instance, in the thermodynamic properties of the order of a few Kelvin degrees between the DFT obtained after reweighting and the deep potential and the deep potential method. So definitely the neural network will never be an exact representation of the reference, but it can be statistically very close.
Yeah, okay. So I understand that. I guess my question more pertained to which model do you deploy in practice? If you have all of these many models and they're quite close to each other, do you choose one according to some criteria? Do you do?
No, they are when we have these different we call that an ensemble of neural network. Essentially, when we have this ensemble of neural network, the spread in the ensemble, when the spread in the ensemble is very small, it is irrelevant which model you use. They will all within the same statistical accuracy. You will be able to describe equally well the system. For instance, here, let me go to this thing here. I think that here this curve, this experiment, this is the theoretical curve. I think that this theoretical curve is actually the superposition of 2 or 3 models. So they are essentially the same for this property. And so the effect when the model are well trained, they describe equally well. So the using an ensemble of model or a few representative model is useful to in the process of training to find out the important configuration in which you need to acquire data to improve your model. But after you have done that, which model you actually use is not important. Still, when you go to very large systems, for instance, I mentioned that we can do a million atom calculation. When you do a million atom calculation, we cannot compare then the result of the model with a DFT calculation because it would be impossible. But we can still see if the network is well behaved in the sense that the spread between the different representative model is still bounded to a small value.
Okay, great. Thank you. That's
You're
good.
welcome. And we have time for one more question from JB Sharma. Would you like to ask your question? Okay, I'll go ahead and read it. Are you able to model and probe the behavior of quasi-crystals in water?
Well, certainly, let's leave the quasi-crystal without the water, and but definitely we should be able to do. I mean, we always use periodic boundary condition in the calculation, so we need to use some approximant for the quasi-crystal, and the approximant for the quasi-crystal will require a large number of atoms. Since we can do something of the order of 1 million atoms, we can certainly study a good approximant for the quasi-crystal. There are a number of things that we can do. For instance, now not related to the quasi-crystal, but related to properties that I think we can access with 1 million atom or we established we were able to do with this summit using the entire machine in test run. We could do 1 nanosecond a day simulation with 100 million atoms. So that's the size of the simulation that can be done with that. So there is a student now doing studying this ferroelectric system, and simpler ferroelectric than the ice, because in the ice the ferroelectric transition is hindered by this ice rule. Instead, in standard ferroelectric like lead titanate or so, the transition is a soft mode, is a displacive transition. So what we can certainly do, we can do this thing with full atomistic simulation. People used, well, David Vanderbilt, my friend David Vanderbilt, Karin Rabe, did very important work in this ferroelectric business by doing using technique that they developed, model Hamiltonian technique, in which they were fitting a model Hamiltonian to the properties, to the DFT properties, but we could do a full detailed atomistic simulation of this model, and we could go one step further because we can go to this very large system and study, for instance, dynamics of domain walls or other properties. What is the effect of having grain boundaries? So a number of properties that were not accessible to this kind of simulation at all now become within the reach, I think.
Thank
Right.
you. That's a great answer. Yeah, just real quick as a follow-up, real quick. So for that funnel-shaped potential that you showed, as the
Yes.
system relaxes, does it populate metastable states in those consecutive wells?
Yes, yes. And we think, well, let me just answer to you and without going to the slides, without chasing the cursor on the screen. Yes, what we think is happening is that there are the order, as you go from the fully disordered state to the completely ordered, the order advances at stages in which you have some stacking of plane, ordered plane or something like that. But we haven't had the time to analyze yet the simulation in detail. So I think that there are some partially ordered structure, metastable order structure along the way. Definitely that is a case. Also, another interesting thing would be to check whether anti-ferroelectric order is also possible. We haven't checked that. The experiments says that it should be ferroelectric in this case of this ICE11, but the other order I structure that are present in the phase diagram that I showed, there are some other that are actually anti-ferroelectric, and DFT calculation, just the ground state at t equals 0, suggest that will indicate that the ferroelectric in the case of this ICE11 is more stable than the anti-ferroelectric. But we can study this thing at finite temperature, and those are all interesting issues to investigate. Yeah.
Okay.
Thank you
All
so
right, thank
much.
you very much. We have to cut it off here. Roberto has another appointment, right?
Yes.
All right, let's thank Dr. Carr for a fantastic talk and questions.
Well, thank you very much. Thank you very much.
Right.
It was a
Thank you so
pleasure.
much. All right, thank
Yes.
everybody for attending, and have
Yes.
a good evening.